Okay, so welcome back, and like I promised, we will come to a bit more advanced. So, we started with very simple systems like FCC, BCC. It is relatively simple. We have seen that they are not really as simple as we thought it to be. Then we moved on to a more complex system like HCP, and there of course understanding is still very limited, and we saw that many things are similar to FCC system. Now we come to not a metallic system, but a ionic system. So, now we will be talking about dislocations in ionic crystals. Now, why am I making a big deal about ionic crystals? It is because there are electronic charges associated with each atom. Now, depending on the type of dislocation and on the plane at which it is moving, there may be a net no charge or there may be net some charge on the dislocation. Similarly, the jogs or the kinks that form, they will also may be charged or neutral depending on what are the particular direction and planes. So, just to give you can say a taste of how it can be different, we are going into this topic of dislocations in ionic crystals. And one of the simplest system that we can think about is NaCl. Now, what is a NaCl system like, or the rock salt, that is the structure that is commonly called. Now, in this rock salt structure, it is what is called as two interpenetrating FCC structure. So, let us look at how it is really it looks like. So, I will have to pay some special attention in drawing this, because it is not a very simple system to draw. So, this is a system where we have what you can see right now. I have not drawn the atoms. So, let me now put the atoms over here. So, what I will do is I will put Na with pink, and this one is complicated not because that structure is complicated, just because I am trying there are too many atoms in one cell that I am trying to draw. So, if you look at just the sodium atom positions, you should be able to realize that this is nothing but a simple FCC system. So, there is atom over here. So, I have drawn it, all the corner atoms and the center atoms. So, this is all our. So, I have all the corner atoms here, I have all the corner atoms here, face center over here, and on the back face this is another corner atom that I was missing, this is another face center atom missing, and again here there is another atom that is missing, and like I said, these are all sodium atom. and what is it forming? If you look only at the structure of sodium atom, it is FCC. Okay. So, now let me draw the chlorine positions, and where are the chlorine atoms? So, the chlorine atoms are over here. Now, just looking at this, you may not be able to realize, but when you draw 2-3 cells, you would see that chlorine atom also forms a FCC structure. So, if you look at this phase, what you see is, you can say this is the beginning of half cell of the chlorine atom. So, this is the phase, all the corner atoms are occupied by chlorine, phase center is also occupied by chlorine, and then again this is another phase over here, and here this is these are the corner atoms, this is the phase center atoms, and if you had drawn another layer, you would be able to see that this is actually the chlorine atom is also FCC. So, this is what is called as so it turned out to be decent diagram. So, it is interpenetrating FCC structure, and like I said, why is it so important? Because here Na is charged plus, and similarly your chlorine is charged like minus, and because it is an interpenetrating system, it is not the usual FCC slip system. So, what is the slip system here? The slip planes for this one are 110, 100, and occasionally if it were a slip, if it were a FCC, then the slip planes would have been 111. But here this is not the case, these are the preferred slip planes, and in some cases you may actually end up seeing 111 slip planes and even 112 slip planes. And what is the shortest lattice vector? Well, that we cannot change, that is still 1/2 110. Okay, so this is again although we are using shortest lattice vector as a/2 110, but then that is what we have not explicitly mentioned, as you will see that there is not just one extra half plane, there are 2 extra half planes. So, what do we mean by that? Let us see. So, again some more drawing over here. So, let me start with structure like this. So, this is our 001 plane, like we said that 001 plane is one of the possible slip systems, slip planes. So, this is a 001 plane, and the directions, if you want to look at it, this will be your 110 in this direction and 1/10 in this direction. So, this can be one of your Berger vector, or this can be a Berger vector, but right now we are assuming this is your Berger vector in this direction. So, there is what we are seeing is that there are alternating layers of atoms with opposite signs. So, now you can see already that this is the structure is unique from what we have seen earlier, and I am drawing only a small part of it, so that I can show you the structure of the edge core. There will be, it does not mean that beyond this there are no atoms, there are atoms beyond that and with similar charge. I am just drawing a small section or some region close to the dislocation core. And moreover, this way it becomes a little bit easier to draw the system. So, that is another advantage when I am drawing it like this. It is easier to remember where do these atoms lie. Now, you see this is your, okay, again I will have to show you the extra, where do the extra half planes lie. So, what you see, and I will delete these lines to make it easier to understand now. So, what do you see over here? This is the structure. Now, what do you see? There are, because there are charges, you see there are 3 planes here and on the bottom there is only 1 plane. So, here 2 planes with opposite charges are missing on the down. So, one thing to realize is that edge dislocation is now clearly different from a non-ionic system, in that you have 2 planes missing. Overall structure, if you look at it, it is like a simple cubic, but it is still not a real FCC. Once you have interpenetrated, then each of them, the total system is acting like a simple cubic, and in that sense you have 2 layers missing, even though it is a simple cubic system. So, this is your dislocation core. And as you can see, this is your where your edge dislocation, you can draw it like this, and the Berger vector would be drawn like this, which is 110, a by 2 110. So, what are the things that we note here? One, that okay, I need to draw another picture. So, I will not write here, I will quickly mention at this point. What we are noting is that 2 planes with opposite charges missing. And now, if you look at it, it may seem at this stage that the core has a net charge, but then what happens in the layer below it? If you go back to this one, this is your, so what we have drawn is a 100. So, these are the alternating layers. So, if behind this there is opposite charge. So, behind each electron, behind each atom, there is an atom of opposite type and therefore opposite charge, and in turn that means that what you will get if you go one layer behind it would be something like this. So, now again I will have to, so these are guidelines that I am drawing, so that I can so this time I will start with minus, over here I will have plus, just before below this so below this plus is minus, below this minus is plus, and so on. So, that is what I am trying to draw here. So, this is the layer just one atom below this. Now, what do you see here? Again we see this is your dislocation core. And I will draw these guidelines for you to be able to appreciate. So, the Berger vector still remains the same, which is our a by 2 1 1 0, and what has happened? The dislocation core, the charge of the dislocation core has reversed. Here it was minus, here it is plus. So, this is one of the effects that alternating layers consist of alternating charges. Now, what so here I have drawn it for 0 0 1 and I am not going to go in detail. Like I said earlier, what I will just note down a few important things about the dislocations in ionic system is that if you were looking at if dislocation was on plane 1 0 0. So, the glide plane here is assuming that 1 0 0, here we are assuming the glide plane to be 1 1 0, because we have said this is also one of the possible glide planes, but then the other glide plane and preferred glide plane is also 1 0 0. So, if the dislocation was on plane 1 0 0 glide plane, I must say, ions at bottom of extra half plane would be of same sign, meaning that whole row of atom would be of same sign. Now, when this is the case, it implies that this type of dislocation can interact with charged particles. Few more things about the edge dislocation. For edge dislocation, gliding on 1 bar 1 0 slip, which is this one. So, this is the plane is 1 bar 1 0, the Berger vector is 1 1 0. So, when the edge dislocation is gliding on a plane like this, the one that I just drew, then there are few more things we can say. No displacement if the line, the dislocation core is not moving along the line, it means that there will be no net change in the charge, or so the atoms of opposite charges would basically not come in contact with each other, or similarly ionized or charged particle will not come closer than its equilibrium position to the dislocation core. So, the no displacement along line, which is what is the case if you are looking just at the dislocation core. If you move along those line, the atoms are there will be no basically displacement, and when there is no displacement, it means that there is no change in the charge. Now, another thing that you will note is that if this is the dislocation line is is in the perpendicular to the plane. Now, if this dislocation line moves over here, there is same charge from here to here to here to here, and therefore, if this dislocation moves over this, it tries to a small kink is formed in this direction, then that kink will not have any adverse or any kind of repulsive forces because of the charges, because the charges are of the same kind, whether it is here or here or here. So, where even a small kink is formed, that kink will have the similar charge as was for the original dislocation. So, this is also what I am trying to say, that there is no displacement, actually I should say displacement of the line of charge along line, implies no effective charge of emergent point, the point which is moving ahead. Which implies that kinks have no charge. We discussed what are jogs and kinks in part 1. So, kinks have no effective charge. Now, another aspect, this is about jogs. Now, when we are talking about jogs, elementary jogs will not be charge neutral, elementary meaning the one atom height, if you look at it. So, again you can go back here, the charges are of different color. So, here it is plus, here it is minus. So, if you have a jog which is one atom height, then its charge changes as you keep moving. So, odd number of steps are there in the jog or odd number of layers in the jog, then it will not be charge neutral, but if it is even numbered, then it will be charge neutral. So, that is why I am writing elementary jogs will not be charge neutral. And implies that it may attract or repel electrostatically. So, this is about the edge dislocations. Now, just again without going into the details, just because we have started this topic, let me write down a few things about screw dislocations. Now, screw dislocations, if it is moving on a 110 type of plane and if it has a Berger vector 110, then it cannot or it cannot cross slip onto any other 110 plane. Can you think of why? So, what I am saying is that if it is on a 110 plane with a Berger vector also of the 110 type, not exactly the same, it cannot be. So, if you have a screw dislocation of that kind, then it cannot cross slip onto another 110 plane, and the reason is that a particular Berger vector of 110 type can be contained on, or that particular Berger vector can only be obtained on one 110 plane, it cannot have more than one 110 plane. So, that is because a 110 vector can be contained on only one 110 type plane. Another important aspect about screw dislocation. So, if you look at the core of the screw dislocation along 110. So, let us look at 110 direction which will be the line direction. So, if we are talking about here, so this is 110. So, this is the 110 direction. Now, what do you see? All the charges, all the atoms are of same type, whether it is Na, in this particular case it will be Cl, again it will be Na. So, it is of the same charge. So, core of screw dislocation has same charge along the length. It implies that displacement parallel to Berger vector results in no effective change of charges. Or no relative change in position of ions. So, these are some important aspects, and as you can see that when you are talking about ionic system, just because it is ionic and we have not even gone into the complexity of stacking fault or the what is called as chemical stacking fault. So, just looking at charges we can see that there are so many complication arising, so many different type of interaction can arise. So, that is just to give you a glimpse of how a dislocation can be inside ionic system. So, that is all we will cover about the dislocation in ionic system. Next time we will come and talk about a more interesting system which is dislocations in superlattices. Thank you.